All right, let's talk about something that's literally all around you, but you can't see it. It's this hidden force that powers, well, pretty much everything. Your phone, that fan in the corner, it all boils down to this amazing dance between electricity and magnetism. So let's dive in. So, have you ever really stopped to think about it? How does an electric fan just spin? Or how does your phone charge up without any obvious moving parts? I mean, it feels a little bit like magic, right? But it's not. It's just some really, really cool physics. The whole secret is this incredible link between electricity and magnetism, and we're going to pull back the curtain and see exactly how it works. Okay, so here's the plan. We're going to start with the basics, how a simple wire can create a push. Then we'll see how to turn that push into a spin. After that, we'll flip the whole thing on its head and see how spinning can actually make electricity. And we'll wrap up with the voltage changer, the transformer, and see how this all comes together to, power your entire life. All right, first stop on our journey, a force from a wire. This is the fundamental idea behind every single electric motor out there. So, this is where it gets really cool. It's all about something called the catapult field. Just imagine, you've got a magnet, right? It's surrounded by its own invisible magnetic field. Now you take a wire and run an electric current through it. Turns out, that creates another magnetic field around the wire. And when you bring those two fields together, they can't just overlap. They interact, they push and pull, and they create this combined, stressed-out field that literally catapults the wire out of the way. It's an actual physical force born from these two invisible fields bumping into each other. Okay, but which way does it get pushed? Up, down, left, right? Well, there's a super handy trick for this, and it's called Fleming's left-hand rule. Seriously, do it with me. Hold up your left hand. Your first finger, the index finger, points in the direction of the magnetic field. Your second, or middle finger, points in the direction of the current. And guess what? Your thumb will automatically point in the direction of the motion. It's like a built-in cheat code for figuring out how motors work. Right, so a single push is cool and all, but it's not going to power a fan. We need that push to happen over and over and over again to get a continuous spin. So how do we take that one little catapult kick and turn it into nonstop rotation? Well, that's where the genius of the DC motor comes in. When you boil it all down, a motor has one job, and it's an absolutely incredible one. It takes electrical energy and transforms it into kinetic energy, or, spinning. That's it. Electricity goes in, motion comes out. This simple idea is, without a doubt, one of the engines that runs our entire world. Okay, but hang on a second. If you just push a coil, it's going to flip halfway and then get stuck, right? The forces would just pull it back. So how do we get it to go all the way around? The solution is pure genius. It's this little thing called a split ring commutator. Check this out. Right at the moment the coil gets to that vertical, stuck position, this clever little ring switches the direction of the current. And by doing that, it flips the forces. So instead of being pulled back, the coil gets another push, continuing the spin. It's this constant, perfectly timed flip-flop of the current that gives us that smooth, nonstop rotation. So we've seen that electricity plus magnetism equals motion. But physics loves symmetry. So it makes you wonder, what happens if you do it backwards? What if you start with the motion? What if you take a wire and physically move it through a magnetic field? Can you make electricity? And the answer is a huge, resounding yes. This amazing concept is called electromagnetic induction, and it's the exact opposite of what we just talked about. By simply moving a conductor, like a wire, through a magnetic field, you generate a voltage, a kind of electrical push. We call it an electromotive force, or EMF for short. Think about that for a second. You are literally creating electricity out of thin air, just by moving something. And this whole idea is wrapped up neatly in something called Faraday's law. The fancy term is magnetic flux, but you can just picture it as invisible lines of force flowing out of a magnet. Faraday's law basically says that the more of those lines you cut with your wire, and the faster you do it, the more voltage you're going to generate. So if you want more juice, you've got 3 options. Move the wire faster, get a stronger magnet, or use more coils of wire. Simple as that. Now, this whole induction thing isn't just a neat party trick. It's literally how we generate nearly all the power for the entire planet. We're now talking about generators. Okay, this is a big one, so listen up. Remember that left-hand rule for motors? Well, since a generator is just a motor in reverse, it makes sense that we'd use the other hand, right? So for generators, to figure out which way the current will flow, you use Fleming's right-hand rule. That is one of the most important things to remember from all this. Left hand for motors, right hand for generators. Got it? Good. And what's really wild is that the type of electricity you make all depends on one little part. If you use a simple component called slip rings, the current just naturally flows back and forth as the coil spins. That gives you alternating current, or AC. But if you use that clever split ring commutator we talked about with motors, it does that same job of flipping the connection every half turn, which smooths out the flow and gives you direct current, or DC. Just one tiny change completely changes the output. Okay, we're at the last major piece of our puzzle. We've used magnetism to create motion and motion to create electricity. But what if you could use this principle of induction to manipulate electricity without any moving parts at all? Well, that's where we meet the unsung hero of our power grid, the transformer. The way this works is just so elegant. You start with AC, alternating current, which is key. That current flowing back and forth creates a magnetic field that's constantly growing, shrinking, and flipping. Then you have a soft iron core that acts like a highway, guiding that changing magnetic field over to a totally separate coil of wire. And because that second coil is now being hit by this constantly changing magnetic field, you guessed it, Faraday's law takes over and a new voltage is induced in it. It's like magic. Pure induction, zero moving parts. And the best part is how incredibly simple the math is. This formula basically says one thing. The ratio of the voltages is exactly the same as the ratio of how many times the wire is coiled. That's it. So you want to double the voltage? Just make sure the second coil has twice as many loops as the first. Want to cut the voltage in half? Use half the number of loops. It's an unbelievably simple and reliable way to get exactly the voltage you need. And this simple idea leads to the two types of transformers that are everywhere. You've got step-up transformers, which have more coils on the second half to boost a voltage way up high. That's what we use to send power across the country efficiently. And then you have step-down transformers, which have fewer coils on the second half. That's what's inside your phone charger, taking the high voltage from your wall and stepping it way down so it doesn't fry your phone. Okay, so let's put it all together. The motor effect, electromagnetic induction, transformers. These aren't just abstract ideas in a physics book. They are the three pillars that hold up our entire modern electrical world. And here's where you see just how crucial transformers are. To ship electricity over hundreds of miles of wire without losing a ton of it as wasted heat, you have to crank up the voltage. And I mean really crank it up. Power plants use giant step-up transformers to get it to insane levels, like 275,000 volts. Then, all along its journey to your house, a series of step-down transformers gradually bring it back down to a safe, usable level for your wall outlets. All right, so if you're going to remember anything, remember this. Motors use current to make things move. Generators use movement to make a current. They're perfect mirror images of each other. And the way to keep them straight? Fleming's left-hand rule is for motors. Fleming's right-hand rule is for generators. And finally, the all-important transformer, it absolutely needs AC to work its magic. And that leaves us with a pretty wild thought, doesn't it? All this technology, the stuff that literally runs our civilization, is based on principles discovered over 100 years ago. It's the invisible foundation we've built everything on. And it just makes you wonder, what's next? What's the next great leap in electromagnetism going to look like? What are we going to discover tomorrow?